Okay, so we're going to continue our discussion of the Bohr model. Now we're going to make it a little bit more quantitative to calculate the energy changes for electronic transitions in a hydrogen atom. So the energy levels that are available to electrons are given by Bohr uh, through this equation. Energy is equal to minus 2.178 times 10 to the minus 18 joules. Those are units of energy, multiplied by the square of the atomic number, so the nuclear charge, the number of protons, over n squared. And n is that integer, that whole number that indicates relative radius from the nucleus. So z is the nuclear charge, the atomic number, which you guys will recall from chapter 1 is the number of protons. N is just a whole number that indicates relative radius from the nucleus. The higher the n, the further from the nucleus. So n equals 1, 2, 3, etc., all the way up to infinity, going in whole numbers. Okay, so again, with the Bohr model, we were talking about these kind of circular orbits that surround the nucleus, and we call them orbitals. Another word for them, a better word for them, is really shells. Shells are the energy levels that electrons can inhabit in an atom, any atom, not just hydrogen. So, as you can see, N increases as we get further away from the nucleus. So, the energy is inversely proportional to n squared, as this Bohr equation shows, right? So if we take out the z and the constant and everything, we see that energy is inversely proportional to n. So what that means is that as this denominator approaches infinity, so as n approaches infinity, you get so far away from the nucleus that there's essentially no interaction of electrons with the atom, and the energy is going to approach zero. Okay, so that's just a complicated way of saying that when you're really, really far away from the atom, you have no interaction of the electrons with that atom. Um, so E equals zero is the reference value for no interaction of electrons with the atom. All right, so how can we put this equation into use? We can use it to answer questions like this one. What is the energy change for an electron transitioning from the n equals 4 energy level to n equals 1 in a hydrogen atom? So going back to the diagram from our previous lecture, here we're asking what happens if we have an electron starting in n equals 4 and it falls down to the ground state, n equals 1. So let's see if we can use Bohr's equation to calculate what that should be. Okay, well, first we need that equation. To solve these kinds of problems, you should really bear in mind that you're calculating a delta E. And whenever we're dealing with a delta E, we are taking the final state, whatever it is, final energy, and subtracting from it the initial state. In this case, our final state is n equals 1. So I'm going to call that E of 1. And our initial state was n equals to 4, right? Because we're going from n equals 4 to n equals 1. So really, my delta E is E1 minus E4. Now I'm going to take the Bohr equation and calculate the energy of each energy level using that Bohr relationship. So here's the constant, minus 2.178 times 10 to minus 18 joules. And I want to multiply that by z squared over n squared. So it's hydrogen. For a hydrogen atom, Z is going to be equal 1 because that's the atomic number of hydrogen. So I'm going to have 1 squared in the numerator. And then the N comes from the N equals 1 here for this final state. So that's going to be 1 squared as well. So this is just going to be the constant, negative 2.178 times 10 to the minus 18 joules for the energy for N equals 1. We can do the same thing for N equals 4. In that case, the only thing that changes is the N value because we're still talking about hydrogen. So it's 1 squared over 4 squared. So 1 over 16. And that is going to reduce that number to negative 1.361 times 10 to the minus 19 joules. So now I can plug these values into the delta E equation. Remember, I'm subtracting E1 minus E4. And that is going to give me negative 2.042 times 10 to the minus 18 joules. Okay, so there are, again, what is this? This is the energy that's going to be released when an electron goes from N equals 4 to N equals 1. It's important to note a few things about this. The negative sign is always going to be when I release energy. Energy is released. Another word for that is emission. When I have an electron fall from an excited state to a lower energy state, it emits light. So it releases energy. We get loss of kinetic energy in the form of light. Now, as a follow-up question, what wavelength will this transition occur at? If I have a detector, where is this going to occur? So you can always interconvert between energy and wavelength because of the relationship that delta E equals h nu, that's Max Planck. And of course, frequency and wavelength are related. So rearranging that, I can solve for wavelength. It's going to be equal to Planck's constant times the speed of light over delta E. Now here, you can't have a negative wavelength. You can't have a negative length. So just take the absolute value, take away that sign. The Planck's constant is 6.626 times 10 to the minus 34 joules seconds. The speed of light is 3 times 10 to the 8th meters per second. And the delta E we just calculated is 2.04 times 10 to the minus 18. I'm taking the absolute value, so I'm getting rid of the negative sign. The joules cancel, the seconds cancel, and I'm left with meters. So 9.735 times 10 to the minus 8 meters would be the wavelength of that transition. Okay, and remember, you can't have a negative wavelength. So in general, when you're solving these sorts of problems, remember that the delta E is going to be the energy of the final N, whatever that is, minus the energy of the initial N. And you kind of plug that into the Bohr equation. The signs might be a little bit troublesome. So one other relationship you can use, just if you're looking at delta E and you're combining two energy levels, is you take that constant from that Bohr equation and you take the N of the final state minus that same term for the N of the initial state. I think that it's always safer to really think about where the electrons are moving to because otherwise you can get yourself confused with the signs. So another trick is that whenever you go from a high N value to a low N, then you have loss of energy. So your energy change should be negative. This corresponds to emission of light. So you get a negative delta E for those situations. And of course, conversely, whenever you go from a low N shell to a high N shell, the opposite is the case. You're gaining energy, and that corresponds to absorbing light, absorbing energy. And that would be a positive delta E.